Hi, and welcome back to Allen High School's discussion of chemistry at the APIB level. And we're talking about how structure and function interrelate with one another and the properties of substances. We're going to be doing first pure substances and then evaluating mixtures. Now, the first one I picked, kind of random, as we talk about structure and function, is electrical conductivity. Conductivity requires freedom of motion or freedom of movement for electrons. So somehow the structure has to accommodate the electron's mobility. So we need electron mobility. Now, with network covalent, we have a variety of network covalent. We talked about diamond, which is one of the allotropes of carbon, Buckminster fullerene. So Buckminster fullerenes, there's a whole class now of fullerenes. And we're going to look at graphite in just a minute, silicon dioxides, silicon, all of these are that ongoing network of covalently bonded substances. Mostly they don't conduct for network covalent, but there are a few that do. And in this case, graphite, you remember how we put carbons at all the bends? So there's carbons here, and then the network is spreading out and so forth. There's alternating double bonds throughout this network. If you'll notice around each carbon, we have each carbon as its own little center with an AB3 structure. So these are sp2 hybridized. The free p orbitals can make those pi bonds. Now, when those pi bonds are alternating like this, we have delocalized electrons. We used that term before. We talk about electrons that aren't bound necessarily to a particular location. And this allows movement of electrons through the network. Now, that doesn't happen with all network covalent. So that's a little bit more unique of graphite, and we'll see that come up in our conversation later in the year. Metals, that sea of electron is critical here. Remember, we have positive ions and we have the valence electrons. Again, we can use that delocalized. It's something of a covalent effect because all of these valence electrons are shared within this ongoing network of metallic bonding. I don't like to necessarily use the word covalent, but it has been used before. But the key here is that these delocalized electrons are free to move. If we have freely moving electrons, they will conduct. So metals will conduct electricity, both pure and alloys. And we'll talk about alloys in the second part of this two-part segment that we're going to end the semester with. So you need to be able to draw, if you look at your objectives, and we need to look at those carefully, you need to draw representations of metals. You need to be able to interpret representations of these bondings structures. You need to explain what it means, and then you have to use it to justify properties. So those are all very higher order thinking skills that we're going to have to invoke for this. And so you have to understand this sea of electron model pretty deeply. So you have to draw those particle representations. We've started with those. Interpret what we mean by those. So here you might want to put in these freely moving electrons. If you want to, that would kind of explain a little bit. What they're trying to show in this picture with these blue is that those valence electrons provide, and this will come into play in a little bit earlier, they kind of provide a buffer or protective region so that the positives don't repel the positives. Okay? And that's what those freely moving sea of electron is doing, is it buffers or blocks, or shields is a better word. There we go. the valence electrons, that sea of electrons, shields the positive ions that are in the lattice from repulsion. Okay? All right, so that's our metallic structure and conductivity. What about ionics? Ionic solids, it depends. It depends on their state. What we find is that if it's an ionic solid, the ions are held rigidly in place, which holds the electrons rigidly in place. So there is no freedom of movement of electrons. So solids don't conduct. So, again, we'll get out some conductivity meters during our lab, and we can show you that the solid, stick it in some table salt, and it's not going to conduct electricity, all right? Now, if we melt the ionics, however, melting breaks apart attractive forces. And in this case, it breaks apart the attractive forces. So as we begin to melt, we start to loosen these ions. And let me tell you, this is for most very high temperatures required to break those forces of attractions in an ionic. And what happens is, what this picture is showing you is that if we set up a negative charged plate here and a positively charged plate here, the ions can move, and those freely moving ions allow freedom of motion of electrons. And so molten or melted ionics will conduct. And then this moves a little bit into the discussion of solutions. Once we put ions into water, so we've got them surrounded by water molecules, and we did this at the beginning of the year. Remember when we wrote our dissociation reactions? That's effectively what we were trying to represent. And so those ions are now surrounded by water, and that provides a pathway. So we have a pathway for electron movement, and so aqueous solutions of ionic substances conduct electricity, and those are called electrolytes. Like Gatorade is an electrolyte. If we put a conductivity meter into Gatorade, it's going to conduct electricity. We would see it register some, I'm forgetting the units. I just lost it in my mind. So resistivity is ohms, and it's going to come to me probably as soon as I end this video what the units are. So at any rate, it does conduct electricity. That's just a silly loss in my mind. All right. Covalence, easy. Covalent molecular substances, again, we're talking about those discrete. It doesn't matter whether it's nonpolar or polar, has nothing to do with it. There's no pathway for electron movement. They do not conduct. Whether they're molten, whether they're solids, whether they're aqueous, they do not conduct, which hopefully you see might be a good way to distinguish between whether you have an aqueous solution that's an ionic aqueous. So this could be a test for us versus, say, a covalent, maybe sugar. So if you have sugar dissolved in water, it's attracted to water, but one will conduct electricity and one will not. So it's a way we can distinguish or identify within a solution or identify an unknown, which would be a fun lab to do. Okay, so that is conductivity. We will end that for now and come back to structural integrity in our next video. So until then, this is... So I hope you had a happy Thanksgiving.